Next speaker is Professor Dimitrios Vamvatsikos from National Technical University of Athens, School of Civil Engineering, Greece. Dimitrios Vamvatsikos has a diploma in civil engineering in 1997 from NTU Athens and a Master of Science in 1998, a PhD in 2002 from Stanford University. He held the position also as a professor at the National Technical University of Athens, where he focused on integrating structural modeling, computation techniques, probabilistic concepts, and experimental results into a coherent framework for the performance of risk assessment of structure and infrastructure subjected to natural hazard. He has cooperated with leading structural engineering firms, the oil industry, catastrophe risk modeler, and the insurance, reinsurance industry. He has co-authored guidelines for Applied Technology Council, the Federal Emergency Management Agency, the U.S. National Institute of Standards and Technology, and the Global Heritage Model Foundation. He's currently involved in the evolution of Eurocode 8, focusing on the seismic design of industrial facilities. So, thank you, Dimitrios. It's a very great pleasure to introduce you, and I leave you the word for the presentation. Given that you have two presentations, so I leave the speech for both, and then I will open the question and answer section.
Excellent, thank you. I will try to be on the quick side. I think we'll easily make up for the time. So the whole idea here is that there's a little bit of discussion on the little things that are left over. And this is typically the ancillary elements in industrial facilities. Now, scope for application in this case, and maybe I should, let's get a pointer. Come on, pointer, pointer, pointer. Excellent. Is essentially ancillary elements in industrial facilities. And of course, what we do not cover is components employing isolators, viscous or friction dampers, components that may respond to sliding or rocking. Kind of unusual, but it may happen. And interaction with other components or the structure itself. And of course, no impact risk. Functioning or process interdependencies, very important thing, but best left to specialized discussions and not just the basic structural design. And what we do cover is essentially non-interacting single support yielding, or if you will, elastic components, and multi-support components, meaning components like piping attached to different points in a structure that may experience differential support movements. So essentially, it's either elements that behave like an oscillator and are subject to mainly accelerations, or components that are hinged at three different Moore spots, and they can be subject to differential displacements. Anything in between, on anything that includes extra things, that's not covered. Now, of course, the first question is why, or why, dear God? Because Eurocode 8 Part 1.2 already includes provisions for non-structural components. If you check out Chapter 9 and Annex C as a very detailed method, well, yes, it does, and we do not want to replicate it, right? The plan is we want to include what is in Eurocode 8.1.2 and let's say augment it, or in some cases, simplify. Now, the point is that Eurocode 8 Part 4, which is where we are right now, is meant for industrial facilities. And industrial facilities components come with a lot of concerns, safety concerns. We have different safety standards, we have different requirements, we have different modes of application. And by that, I mean that ancillary elements may be upgraded, replaced, or modified throughout the structure's lifetime. Because essentially it's about the components more than it is about the structures in many situations. And the problem is that a guy coming into the discussion 10 years after a structure has been built, to ask him to redo the whole structural analysis, to replace a single component and define its design values, that's kind of difficult sometimes. And it's something that has been faced in practice. Now, the whole idea is we need some flexibility in designing the supports of such ancillary elements without necessarily reanalyzing a full structure or undertaking any kind of health monitoring, operational model assessment, etc. Now, we also need some simplicity. Why? Because there's a lot of components, and allowing an engineer to go a simpler way usually pays off. And also, there is the other problem, uncertainty in structural characteristics. you can apply a very good scientific method if you know everything that you need to put in there. If you start having second thoughts, or if you do not know what needs to go into the discussion and into the formulas, then it's trouble, because theory and practice, they can diverge there very, very wildly. Now, just to give you an idea, here's the basis of design for this. In general, your design must account for the ancillary elements, easy. They must account for the connections of the elements of the supporting structure, makes sense, and of course, with any interactions with the supporting structure. Now, impact among components or components and structure should obviously be eliminated by providing adequate clearance. I'm saying this because we have to say it. Partial safety factors, of course, they would conform to Eurocode 812 because we want to be compatible. Now, modeling-wise, 3 different cases. If your structure and your components interact statically or dynamically, you need, of course, to model the structure and the component. I'm sorry, there's nothing I can do about it, okay? You have to do both. Why? Because obvious reasons. Anything else you do will not be exact to the situation. There may be some concepts of if it has relatively low mass, or anyways, there can be some simplifying assumptions, but I don't think they're, let's say, general enough to be able to put them here. So that's the tough one. Now, if your component interacts a lot with your beams or the floor that it is based on, but it does not influence the entire structure, then you can escape by modeling the supporting elements and the component itself. This would be the case, for example, for a flexible beam or a flexible floor, supporting a component and being vulnerable, for example, to vertical accelerations. There are cases like this. In this case, there is a chance that the component amplifies the deformation of the beam or the supports in general, so you need to be able to have a model of both. But you don't have to model the entire structure usually. Now, there is also the issue of having just the component itself, and this would be the majority case for components that do not interact dynamically with the structure. For example, components of relatively low mass. And let's say this is business as usual. Again, I will differentiate 2 cases. Will be the single support components, where essentially you are designing them as subject to floor acceleration spectra. That is essentially Eurocode 812, if you will, and the extras will show here. And then there's the multi-support components with negligible vibrations, because if they vibrate, they're heavy, and they also vibrate, you need to go to the earlier, tougher modeling options. If they're just an extra added stiffness between different supports of the structure, different floors, you just need to design the component, give subject to the differential support deformations, which you found by analyzing the structure. So again, this third version is the one we will mostly deal with. The other ones, unfortunately, you need to model things and take matters in your hands. Now, how are you going to do the analysis? Well, if you're going to be modeling, of course, it depends on what you're modeling and what you're analyzing. If your model is the supporting structure and the component, that's the tough case. You can use MRSA, response history analysis. If your model is supporting member and component, then MRSA response history analysis, or potentially you can also use an equivalent static analysis, given that you have figured out the component support spectra. So the spectra of motion, if you will, the absolute accelerations at the supports of the so-called flexible beam or floor underneath the component. And the typical case is the case where you have only a component to figure out. And in those cases, you can use MRSA, you can use ESA, and typically you use floor spectra, if you will. And this is the case, and this is where we're going to focus. Okay, so from now on, I will only be discussing single support components, ancillary elements, if you will, and I will assume that what we want to do is an elastic, static, equivalent static analysis. Now, brief introduction to the problem. It's the classic one where you have a structure, you have components nested into the structure, you are shaking the ground, and that will be a peak ground acceleration entering the structure. Of course, it's a whole time history, and then it goes through 2 cycles of amplification, or 2 stages of amplification. Actually, I should say modulation. Modulation is the right name for the game, because if the periods match, of structure and component, for example, structure and soil, but that's another discussion, then you get resonance and you get an increase. If they do not match, you might as well get an amplitude decrease. So your PGA, your peak ground acceleration, essentially becomes peak floor acceleration, which then hits the component, and it's modulated, of course, by the element itself and becomes peak component acceleration. And it's for that acceleration that you want to design. In general, resonance is the enemy. Once you hit resonance, you can see a very substantial increase in amplitude. And the one thing you have to remember is because this is a highly elastic problem, this problem of resonance, it's very, very sensitive. Essentially, you must know periods of the structure, you must know period of the element, damping ratios, because these tell you how much the amplification is going to be. And of course, you need to know whether any of the two develops any inelasticity. Why? Because inelasticity, if you will, is our friend. It's the enemy of our enemy, is our friend, yes. Inelasticity manages to detune the structure by introducing some wave delay, and then it removes resonance, or really, really de-amplifies it. We'll discuss it later on. In general, unless you have perfect tuning and elasticity everywhere, resonance will probably not happen. Now, here are the three methods we are proposing for design here. The method one is essentially what Eurocode 812 says. It's the one that is already in there. It's non-dissipative, except there is a little bit of a component behavior factor that you can include by roughly taking account of the component and its anchorage being able to dissipate a bit of energy by going inelastic. It's kind of complex, but it's also quite accurate in the sense that if you know periods, mode shapes, if you know everything, it actually gives you really good results, and I'll show you an example later on. There's also method number two. This is the non-dissipative method, if you will, of Eurocode 8 part 4. And that's a non-dissipative method again. It's simplified and quite conservative, as you will notice in the bit, but it assumes imperfect knowledge. And it does that by saying, yep, resonance is going to happen. Everything is more conservative. Worst case scenario, catastrophe, etc., etc. Be careful. Method 3, again, is the dissipative version of Eurocode 8 part 4. That's what we're going to propose in this case, which requires a fuse with certified overstrength and ductility, and everything else is over design, meaning that the fuse that you put in the load path of the structure to the element, to the component, if you will, allows you to take advantage of detuning and removing any possible resonance. In this case as well, imperfect knowledge about anything else in the structure and the component is okay, but the fuse has to be certified, meaning you cannot just take any piece of steel and call it a fuse. Now, that's method one, and I'm just putting the basic, not all of them, the basic equations, and you can see it's no piece of cake. First of all, what you see here, you repeat for every mode of the structure, which makes sense. If a structure is multi-mode, resonance can happen in any mode. All of these responses need to be added, right? Modal response spectrum analysis. You must know the periods and the mode shapes. Have fun. And you also need to know component behavior factors if you can. There's a proposal. You need gamma i's, mode shapes, periods of structure and component, etc., etc. Oh, and also the structural ductility, which it could be a bit haphazard in some cases, but yes, you need to know the ductility of the structure that they can reliably introduce into the response. And of course, damping ratios, and all of that you need to know for every single mode. And that is potentially trouble. Now, simple but conservative is method 2. Now, in this case, you're only considering a single mode, just one mode, and that's it. And you might see the big difference is that there was a certain I over here, which indicated mode 1, 2, 3, etc. This is gone. You just go with mode number 1. And of course, because there is a price to pay, there's no free lunch, the amplification at resonance predicted by method 1 is taken here, and your component damping is taken low at 2%. You assume, if you do not know your mode shape, well, assume a linear shape, pretty much as was done before in Eurocode 8. And you do not allow any reduction for inelasticity in the structure, regardless of what consequence class or ductility class you designed it, because unless you verify it by a pushover of some real inelastic analysis method, you cannot use it. Why? Because, as you may know, a lot of the initial behavior factor, let's say a lot of the initial response of the structure, is essentially not governed by ductility, but by very, very high overstrength. And overstrength is the enemy, as you will notice later on. In general, this is a very conservative approach. It assumes the worst possible thing, but you don't need to know anything much, just basic stuff. Of course, it comes with a price, higher design forces. Yeah, just some basic stuff, but all of this, you get simplified assumptions for it. Now, method 3 is the fuse for the win method, meaning you have a fuse, a structural fuse we discussed earlier, and you might notice as I'm going forward, the number of equations decrease and decrease and decrease, because you're only considering one mode, and you just have to define a peak floor acceleration, sure, multiply by the amplification factor, sure, easy. And then the amplification factor essentially is just a very simple equation, because that's what we found analytically and has been found, actually verified several times, that if you include the yielding elements in the load path, it makes your life a lot easier, because it disengages your structure and your component, and also removes the need to know a lot about the structure and the component, because yielding takes care of resonance. Now, it's highly reliable. It also reduces a lot the design accelerations, meaning it allows your component to remain functional if you need it after an earthquake, safety critical stuff, remember. And also it allows low anchorage forces to be transmitted to the structure. There is a requirement, meaning that the amplification can go as low as 1.3 in some cases. Now, minimum ductility for the component is 1.5, which has to be certified, designed by testing, if you will, by the manufacturer. Also, overstrength has to be low. Otherwise, who's gonna really believe that this ductility will ever happen, and detuning will happen because you need it. And if you want to increase your reliability, meaning account for higher importance components, the important thing to remember is you do not change anything here. Your calculation method remains exactly the same. The only thing that changes is that you certify for a higher ductility. So MD, essentially, the ductility that you use for your calculations is a nominal ductility, let's say higher than 1.5, of course, it goes up to 3. But if you want to use it and say my component is important and I want higher safety, make sure that it allows higher ductility to take place than you originally assumed. There's no chance overstrength, because remember, overstrength in such a capacity design approach can be the enemy, okay? Now, to make this a little bit more substantial, I'm going to show you a brief example of a case study we've tried. And this is an equipment supporting reinforced concrete moment resisting frame. The plan is about 15 meters this way, about 8 meters this way. Very simple. It's a typical refinery building. And we've put some horizontal vessels, heat exchangers, a vessel, a pump, just to have fun. Now, of interest, of course, is the first and the second floor. And we're going to check what kind of equipment accelerations can go into these. This is located in Elefsina, Greece, 3 major refineries in that area. If you went by the old Eurocode, you'd be having a design PG of about 0.24 G. New Eurocode is 0.71 SA ref, as alpha ref. To help you out, this is the plateau, essentially. Okay, so it's roughly 2.5 times this value. Consequence class 3A, a performance factor of 175 to raise everything to 2,500 years return periods, meaning your plateau now is 1.24 G, which is quite substantial. Ductility class 2, moderate ductility, and your periods in both directions are about the same, about 0.2, 0.21 seconds. I should go without saying, but such structures are heavily over-designed for fireproofing. Fire is the governing situation, it's not earthquake. So the structure is essentially expected to remain mostly at least. Now, to do this properly, we selected ground motions. By the way, the components are also important, so they get an additional 1.5 overstrength Any additional overstrength we disregard it completely because, well, as we all know, there's no 3.5 bolts. You will have to put 4. So yeah, let's forget that one because uniformity impacts all methods. We're going to use response history analysis. Now the records are shown here. And what you can see is the, with a dash, the red dash line is the Eurocode 8.1 actual design spectrum. And over here, you can see the median spectrum achieved by the records, which, by the way, were matched in this region. Okay, they were actually matched not just to the design spectrum, but they used the so-called conditional spectrum approach to accurately match them to the hazard, meaning that a very good representation of what we expect to happen in these periods and for this specific site. Now, just to give you an idea of how the structure behaves, if you're looking at the method 1, here is the average or the median actually response of the structure. This is normalized to the period of the structure. So this is 1, means this is 0.2 seconds essentially, the start of the plateau in most cases. And you can tell how the records behave because you start seeing a resonant peak for a component that will be exactly tuned to the structure at 0.2, 0.21. And over here, about 1/3, 1/4 lower, you start seeing the second mode. Method 1 has excellent accuracy. I mean, you can see it, it captures the second mode, it captures the first mode. Okay, it misses by a bit. You can see that there is a certain amplification of some records. So about 50, maybe 60% of the records can go higher. But still, again, remember, this is a very, very special situation, a very rare situation. And even if you develop any bit of little ductility in there, which you may as well do, or slippage, this will reduce. So I would not consider this to be a problem, okay? Higher modes are also captured and it nicely envelopes. Okay, it misses a little bit here, but who cares? This happens. And the whole idea of we do not need to be super conservative, it makes sense. So I'd say this is a success. There might be some localized peaks again. You're expecting something of the order of application of 2 and you're getting something of the order of 7. But this is 1 out of 30 ground motion. So it's kind of a specialized situation. It can happen, apologies. Without response history analysis, predicting such peaks is essentially impossible. So let's say this is my message. If you really want supreme accuracy or supreme safety, unfortunately, some response history analysis need to be done. I see no fault in method 1 in the ways that it's done. So good job, Eurocode 8 part 1.1. Now, the code is not magic. Some rare events will happen. The only problem, by the way, this is the second floor, this is the first floor, second floor, similar ideas. It predicts everything very, very well. Now, here are the fragilities, essentially the probability of collapse of, if you will, component damage in this case, which may lead to some leakage and fire, in terms of peak ground acceleration. And you can see that the black line is, let's say, our baseline assumption of resonance. Most cases, with some exceptions, in general, you have very, very good results. If you are in tune resonance, what you get is this pretty good value, which for the design value of our structure, it's less than 10% probability of failure, which is even actually less than 7%. I should so remember it was around about 0.4, 0.24 G, maybe even times 1.5, 1.75. You're somewhere over here. So method 1 is doing quite well, even when you're in resonance. If when you are outside of resonance, of course, it's a bit more conservative, with an exception of this. Sometimes there are some periods, okay, actually 1.5, 175, because of those peaks you saw earlier, that just fluke, rogue wave motions that you can have some exceedances. But again, you're talking at really high peak ground accelerations of about 1, 1.2. Now, those are large, too large. Method 2. Remember, method 2 is the ultra-conservative one where you pretend you don't know anything about the structure, and this is true. If you're in resonance, you more or less get the same results as before. Anytime you're not in resonance, you have just over-designed. Why? Because you actually said that I know nothing about the pillars of the structure, I want to over-design. So again, remember, this just means that you may have to have an anchorage force of, let's say, 50 kilonewtons more or 150 kilonewtons more, something of this order for most components, sometimes even just 20, which is a few extra bolts, nothing crazy. So even though this seems like it's a huge conservativeness, it can be taken care of very easily. Method 3 now, and that's the fun. The concept is that you can use different ductility levels, but you must certify them. In this case, because these are important components, you want to certify them for 1.5 times higher ductility than the one you're going to nominally assume. And the fun part is that if when you increase your ductility, this is not meant to increase safety. Increasing ductility is just meant the nominal ductility. Okay, that's not for safety. Only the introduction of gamma alpha P, meaning ductility that you do not use in your design, can increase your safety. Actually, when you increase your ductility, the nominal ductility you design with, the idea is that you decrease the forces and accelerations, meaning you protect better the components. Method 1 and method 2 cannot do that because the amplification factors can go as high as 7. That's it. That's the physics of the game. This one, by changing the physics, if you will, through yielding, it can reduce them quite considerably. To give you an example, if you assume a ductility of 1.5, this is where you go. Your median, if you will, or mean acceleration amplification is of the order of 2 point something, 2.5 maybe. If you go to higher ductilities, this goes further down to 1 point something. And if you go further down again, it goes to almost 1. And this trend continues, but you'll notice that we've put a maximum of 3, ductility of 3 that you can employ, because after a while, what it means to have a ductility of 5 in a component, you may get it, you may not, it's just pushing it too much. Now, one more. This decrease is substantial, but to be sure, we used the 90 percentile values, meaning we didn't go to the black line, we went to the blue and above, meaning you want to capture those peaks just to be extra safe, certain. Why? Well, because once you start putting certified stuff from a manufacturer in there, you expect to get something better. So just to be sure, we wanted to make this a little bit more safe than method 1, intentionally. And we went to the high peaks, way beyond 50% or 84 percentiles to about 90%. Essentially, this means that for a ductility of 1.5, you get an amplification of 3.4, your peak floor accelerations. At 2, you get about 2, okay, that's fair. And at 3, you actually get 1.3, and that's the maximum. We do not allow you to go less than 1.3. If you want to go lower and further protect your component, please use base isolation. That's a different part of the code. And by the way, you can just isolate the component and you don't have to isolate the entire structure. That's also doable. Just to give you some idea, here's how the fragilities look like. In general, look at the black line if you want to see what it means to be in resonance. And you can see that it's, again, a bit safer. Remember, method 2 and method 1 would go a little bit higher up here. So slightly easier to do damage. In this case, resonance works pretty well. The one out of resonance, actually, you're going to be conservative, but that should be expected. Remember, you're assuming you know nothing about the structure. If you go for 1.5, we have to be a little bit more safe. That's what comes out. If you go to higher ductilities, you're closer to the edge with some minor exceedances in some cases, just a few cases where not everything is perfect, but in general, it works. And remember now, you know only the component mass in this discussion, nothing else. But you had to certify the fuse. So win something, lose something. And putting it all together, this is what you get, is you have all your fragilities, all your methods, and we're just showing here the design force, normalized by the mass, if you will, that's a seismic coefficient for the component. And for example, oh, by the way, I've also tried a couple of different approaches. The star version just is a case where I used an approximate mode shape, just for fun. The general idea is that if you're out of tune, method 1 is the best because it gives you really, really low values and it takes care of out of tuning. It knows that you're out of tune. You have supplied it with the proper periods. everything works. If you're in tune and you're working with an elastic method, actually all methods work pretty well. Now, if you're in tune and you're working with method 3, it is the only one that can lower your design forces. But if I had ventured to the left or right of this out of tuning, I would be paying a price, okay? Actually, I am already paying a price because somebody has to make that fuse and I have to buy it. And that might be expensive. I have no idea. Now, as a conclusion, all 3 methods are viable. You just need to make sure to respect their assumptions. And most importantly, I have to say this, please do not assume that you know the period just because you have a model and your model says the period is, I don't know, 0.2 seconds. The reason being that if anybody has done operational model analysis and health monitoring, you know that periods can be quite fickle. There are no single period. There is a low amplitude period, there's a high amplitude period. They change with time, they change with damage, and they're tough to figure out. Again, also, if you want to use a method style of 3, please do not assume that any piece of steel can become a fuse. Make sure you use something that is certified or you're guaranteed to develop what you want. And be careful, because if you do ductile design, you should not think over strength, you should think over ductility, because over strength can be the enemy when you're discussing the fuse, of course. The other elements, feel free to over design as much as you want. And with that, please have some fun and stay safe with Eurocode 8 for 2022 version.